All right. So, second attempt here. So, in this particular problem, we have a car that uniformly accelerates from left to right. It reaches a speed of 20 meters per second by the time it covers 300 meters as shown in the diagram. Okay, so it starts at rest. Its initial velocity is at rest, which is 0 meters per second. Its initial position is also given as 0. So it makes things a little easier. The acceleration is not given to you. It just says some uniform acceleration, but the quantity is not given to you. So here's part A, B, C, D, E, and F. Again, if you like, pause the video, write these parts down if you need it for practice. All right, let's now go ahead and knock out all these parts. Part A asks you to find the instantaneous velocity, v of t, at 2 seconds. V of t here is just a alternative way to find vf. So anytime it asks you to find instantaneous velocity, really it's asking to find vf in the kinematics equations. All right, so in order to do all these parts quickly, hopefully you have these kinematics equations memorized or familiarized. It'll just expedite the process, okay? To find VF, average acceleration is equal to VF minus VI over change in time. To get VF by itself, first you got to multiply both sides by delta t, and then you need to move this negative VI to the left side of the equal sign, which will produce a function that looks like this. So VF is equal to A times delta t plus VI. Here we can just cross out VI because it starts at rest. We can plug in t is equal to 2 seconds. However, a's are unknown. The problem just tells us a is constant, but it didn't give us what the value is. Well, that's okay. So just go solve for a using a different kinematics equation. So in order to solve for vf, we need to know a, but to solve for a, we can use this kinematics equations that is time independent. So here we have vf squared minus vi squared equals 2a delta x. Vi is 0. And then from here, we can just solve for a. To solve for a, we simply divide both sides by 2 and delta x together. And then here, in the step, I substituted the vf, which is 20, which is given in the problem and in the diagram. Vi, I'll just cross out because vi starts at 0. Here, delta x is 300 because by the time it reaches a speed of 20 meters per second, it has cover a distance of 300 meters. In this case, distance and displacements are the same magnitude because the diagram is just going to the right. So delta x is simply just 300 meters, just the magnitude. If you punch out in your calculator, you should get a value of a is equal to 0.667 meters per second squared. And then once you know a, or the magnitude of a, you can simply plug it back in for the final velocity function that we just derived earlier. So vf would simply be a times 2, but we just found a, so a was just 0.667 times 2. That would give us an answer of 1.334 meters per second. And because I asked for velocity, which is a vector, you do need to provide some sort of direction according to your professor or instructor. East would be lovely, or a rightward, or a positive sign in front of the 1.33 would be sufficient. All right. Let's do part B. Part B asks to find the instantaneous speed. Notice here the wording is a little different. Speed would imply that it's a scalar, aka the absolute value. That's just fancy for saying do not provide a direction. Just find the magnitude. So speed is a scalar. There's no need for direction. So how fast is it moving by the time it covers the first 150 meters? So at the midpoint of the distance, not time, the midpoint of the distance, from 0 meters to 150, how fast is it moving? So in order to do so, we can use, again, the kinematics function that is time independent. Why? Because we know vi is 0, and we're just trying to find vf. We already know a from part A, which is 0.667. We know delta x, which is specified here in part B. So delta x is just 150 meters. So you notice here, there's no unknown to really tamper with. Our only unknown is the variable that we're trying to find, which is vf. So therefore, to get vf squared by itself, to get vf by itself, we need to square root both sides. So therefore, if you multiply the right side of the equal sign across, you should get a product of 200.1. And then to get vf by itself, we square root both sides. Square root of both sides will give you a value of 14.15 meters per second. Okay, and again, it asks for speed, so you don't need to provide a direction. All right, so here is the other way to do it. We also know from part A that final velocity can be calculated using A times delta t plus vi. In this particular instant, vi is 0, so we can leave vi out of the function. We know A, which is calculated in part A, which is 0.667. We don't know how much time it took to cover the first 150, but that's okay. Okay, you can find your time. Your displacement function allows you to find time because it has the variable t in it. Here I've chosen to use the displacement function to find time, which is your unknown. If you decide to employ this strategy, we know delta x, which is 150, we know vi, which is 0, and we know a. So really our only unknown is the t variable. So I'll go ahead and plug and check here. Okay, our displacement is simply 150. Our acceleration, which we got from part A, is 0.667. Here t squares are unknown, so to solve for t squared, we multiply both sides by 2, and at the same time divide both sides by 0.667. So if you do that properly, you should get that. And then if we simplify that, to solve for t, we square root both sides. So the square root of 449.78 will give you a value of 21.21. Now, once we know that, we can just plug it back into the v final function, because the only thing that was holding us back was delta t. Well, we just calculated delta t, which is 21.21. So here we just plug and chug. We carry the same step down, except instead of delta t being unknown, we just calculated it, which is now 21.21. And if you multiply that, that should give you a magnitude of 14.15 meters per second, which is the same answer as on the left side. And this is, again, just to show you there are different strategies in terms of finding your unknown quantity in physics. It all depends on which approach you want to proceed and how much work you want to perform. So here's instantaneous speed. I don't need the direction. All right, let's move on to part C. Part C asks you to find the time it takes to reach the 300 meter mark as shown in the diagram. So to do so, again, I think the easiest way to do it is just use your displacement functions, because there's a lot of information given to you. Your delta x here in this case would be 300 meters. I'm just going to use the magnitude, because when you do your math, the direction for this problem doesn't really matter because it's only moving one way. Vi will get crossed out because it starts at rest, and then a is known, so the only unknown variable here again is t squared, which is what we're trying to find, because part CS is to find the time it's required for the car to speed up to 300 meter mark. Okay, so to do that, multiply both sides by 2 again, like in the last work, and then at the same time divide by 0.667 to both sides, and then we do that, and we should get this kind of busy looking thing on the left side, equal sign. And then to solve for t, we square root both sides, and then the square root of 899.55 would simply give you an answer of about 30 seconds, so 29.99 seconds. Okay, and if you don't like that, and if you want, you can use the average velocity function. I do want to emphasize that you can only use the strategy when acceleration is constant, which it is for this problem. So you can't use this if it's a calculus-based physics course where a is not constant. Okay, so for this one, a is constant, so you can set the average velocity functions equal to each other, and this is what it would look like. But you're trying to find t, but t is in the denominator on the left side, equal sign. So we need to make sure it's in the numerator. So to get t in the numerator, simply flip both sides of the equation upside down, and then from here we know vi is 0, and then to get delta t by itself, we multiply both sides by delta x, so it'll look like this. Okay, again, vi is 0, and then multiply both sides by delta x, which looks like this particular function here. And here we know a bunch of information. We know vf, which is given in the diagram, which is 20 meters per second. And then we know our displacement is 300 because the problem specifically states and asks for the time required to reach the 300 meter mark. So delta x here would be 300. And then if you do your calculator work, your time will come out in this work a perfect 30 seconds. Again, due to rounding in the previous strategy, you get 29.99, but really 29.99 and 30 is pretty much the same in my world. Okay, all right. Here's part D. Part D asks for the car's position at 5 seconds. Because it asks for the car's position at 5 seconds, x of t triggers xf. In order to find xf though, I think the easiest way for part D is just to bust out your displacement function. Why? Because you can break up delta x into xf minus xi. And for this particular problem, xi is 0, so that kind of makes things easy. Vi is 0, that makes things easy as well. So again, cross out things when things are 0. And really, you have xf is simply 1/2 at squared. Well, you know what a is from part A that we've been using for the last few parts. And you know t here is 5 seconds, which is given in the statement. So it's just really plug and chug. A is 0.667. T is 5 seconds, and don't forget the square term to carry that down. And if you do your calculator work, you should get that your final position is at 8.34 meters. Now, I do want to point out, position is a vector, and according to this diagram, the car is moving to the right. So the proper way to express this answer would be 8.34 meters, comma east or comma right, or use a plus sign to indicate that you know that position is a vector and that it is to the right of the origin or your starting point. Okay. All right. So let's do part E. Part E asks you to find the ratio of your position at 2 seconds and your position at 4 seconds. And to do so, you need to calculate two things: your position at 2 seconds and your position at 4 seconds. And pretty much it's done after that. All right. So let's go ahead and employ the displacement function again. Again, I left out xi. X of t at 2 seconds is simply just xf, kind of written properly here. Xi is 0, so I don't need to write that down. Vi is 0, so I can cross that out, and I'll just carry down the 1/2 at squared. I know what my a is, I know what my t is, because t is 2 seconds in part E, so therefore I can just plug in values. A is 0.667 again, t is 2 seconds, we'll square that, punch that in your calculator. You should get the final position is 1.334 meters to the right of the origin at 2 seconds. So that is exactly where the car is after 2 seconds gone by on the number line. Okay, well, that's the first quantity we need to find. But the next thing we need to find is your final position at 4 seconds. So we would use the same strategy, except the only thing difference here is 4 seconds. So you notice here the work is side by side. It looks exactly the same, except the only difference is at the time. The time here is 4 seconds. So if you plug in 4 seconds and you do your calculator, your final position after 4 seconds is 5.336 meters. So after 4 seconds of motion, if you were to pause the car's motion or take a picture of it, it should be at 5.336 meters on the number line. But you're not done yet. So you still need to carry down this expression, blank x of 2 seconds is equal to blank x of 4 seconds. So carry that down. But I encourage you to replace the blank here in this statement with just a heart, aka your unknown, or you can do whatever symbols you want or shapes you want, and then just plug in the values that you just calculated. You just calculated here x at 2 seconds is 1.334, x at 4 seconds 5.336. In order to get x by itself, which represents the blank, you would simply divide both sides by 1.334 to get x by itself, and if you do that properly, heart is going to turn out to be 4. So that is your blank. So we say 4 times x at 2 seconds is equal to x of 4 seconds. And that makes sense to me. Okay, so we need to play that back. All right, part F though asks you to find the ratio of your velocity at 3 seconds compared to the velocity at 6 seconds. So we would use the same strategy as in previous part E, except in this case we need to find v, not x. So to find v of t, again, this notation v of 3 seconds is a single point. That tells you just to find vf. And to find vf is at plus vi. Vi is 0. I'll plug in a because we know that. I'll plug in t, which is 3 seconds because it's given in the first statement here. And calculator work will give you a speed of 2 meters per second, or a velocity of 2 meters per second east. Okay? But we need to do the same strategy to find the velocity at 6 seconds. So the only thing difference, once again, is the time. Acceleration stays the same. Instead of 3 seconds, we now have 6 seconds. So if you plug that in, we would say that the velocity at 6 seconds, this should not be a 3, this should be a 6. Okay, so if you're paying attention, my apologies, this should be v of t at 6 is equal to 4 meters per second. So once we figure those two values out, we can just carry the ratio statement down. V of t is equal to 3 seconds is equal to blank. V of t equals 6 seconds, which is here. And then replace the blank with a heart, and then just rewrite the statement. We just calculated v of t at 3 seconds is equal to 2 meters per second, and we calculated the velocity at 6 seconds is 4 meters per second. And then here, to solve for heart, we simply divide both sides by 4. So 2 over 4 is 1/2, and 1/2 is the same as 0.5 in decimal. Or you can just leave it as 1/2. It doesn't really matter. So the ratio is 1 over 2. Okay. All right. Other than that, I hope that helps. Stay nerdy. Don't be whack.